screen. Okay. So just a very gentle reminder that we will be having deadline for the homework too, but by the end of Friday. Okay. So I hope I see most of you have submitted, but please make sure that you submit on time. In the case that you need to change your submission, just email the TA. Okay. So because TA think that's easier for him to handle. So whenever issue with the homework, so please contact TA directly. If you email me, I just forward your email to him. So today the goal is to finish this random variable. I mean, if not, then we prefer stay, but I guess most of we should be able to finish everything here. So very quick review what we have done so far. So just remember the random variable actually means that we are putting a number to a outcome of the random experiment, right? There's a random experiment, the random outcome, some outcome comes out, and then we put numbers to it. And in our course, we focus on putting one number, okay, only, okay. And you can easily see that sometimes it's appropriate to put more than one number. You want to put 2 or 3 or more numbers, right? For example, you look at the stock market performance. You can look at Hang Seng Index as a single number that only representing the whole stock market, right? But sometimes you really want to look at individual stocks. That means that you are not looking at a single number, but multiple numbers. The math is fairly the same, but we don't talk about those because the calculation of variance, covariance, or those things are somewhat beyond the scope of our class. So if you learn further, second course of the statistical, we cover those. And we focus on single number random variable. And depending on what kind of number you are assigning, right? If you assign integers only, then we call it a discrete random variable. If you put a real number, a decimal number, then become continuous, okay? And based on discrete, we have a different way to summarize it, either the probability function or the cumulative functions, right? The P and the P function and the big F function. And we know how to plot those. And based on the P's, we know how to define expectation, which is the mean, right, of the if you repeat this random experiment and each outcome you map to the random variable, this is the mean of the random variable, right? And then if you look at the variance, the same idea would work out. I mean, you can easily see, you can define kurtosis or skewness. That would be absolutely no problem. But again, we would not talk about those in our class because of that would be beyond your scope of our first class for your statistics. And after that, we consider the case of many ways of doing the discrete distribution, right? So the main thing we learn is Bernoulli. And when you have repeating the Bernoulli nth times, and each repeat is independent, then we have binomial. And binomial is the building block for many things. As we will study a lot of time later, remember the binomial is the things that we will continue to work on. And Poisson will be a special case of binomial when n is very big. P is very small, but NP is still n times p is still a fixed number lambda, right? Then it is Poisson used to model how many events within a period of time, right? So that would be the idea. And then we learn hypergeometric, and you compare binomial and hypergeometric is basically saying binomial is you are repeating sampling with replacement. So put this like draw a ball out of the urns, and after every draw, you just put back the balls. But hypergeometric is used in the case where you don't put back. So each draw is dependent on what have been drawn. And of course, if you notice the proof, or you notice that if the sample size is very large, okay, or the ball in the urn has a lot of balls there, whether you draw pretty back doesn't really matter. Okay, but when the sample is small, then it's matter. That's why when you do audit, that would be, or quality control, that would be useful, because you are usually doing a small sample, right? You're not doing the big sample, especially when you do quality control, you have to destroy the item, right? Suppose you want to test whether a fall test, right? You want to drop down the iPhone, right? From what's the height from there, then you, after the sampling, you destroy the item you're doing. So that's why you don't want to do large sample. That's the reason why sometimes you have to focus on small sample, because doing a large sample is expensive, right? Same as doing medical tests for drugs, right? You want to do a drug test that actually you don't, not just cost-wise, but also some reason that you don't want to do a lot of sample, because I mean it's a matter of life or death. Okay, so you don't really want to. You want to be very cautious. Okay, so these are the common, and binomial we'll keep using, because a lot of time we do survey, we ask yes/no question, or where they do or they don't, and that something is important. So we will be talking about yes/no thing for the rest of the whole course. Okay, so binomial, probably didn't remember. Poisson hypergeometric, we will not coming back. Okay, so just you learn the applications of them, then it's done. Okay, and if you learn advanced class, then you probably spend a lot of time on Poisson, basically the whole class. Half the class would be Poisson if you study, say, stochastic process and things and more. But that's much I want to say for discrete. And the all are just basically summarize, or go to the details. And and today we will talk about continuous random variable, right? That is the goal of today. And for continuous random variable, what we want to do today is to continue what we have done. Okay, just to remind you how to describe a continuous random variable. Remember this discrete version, you have the big P and the big F. Okay, and here the big P has no meaning. Why? Big P tell us what? For discrete cases, you give me a number, okay? Then I tell you what is probability that the random variable equal to that number, right? And in this case for continuous, there's no point of that. Why? Because the random variable can be many numbers, right? Because continuous, which means, let's say, a random variable between 0 to 1, right? And how many numbers are between 0 to 1? Infinite many, right? The many, right? Because whatever number you give me two numbers, anything in the middle is still a number, right? So that's why there's infinite many, right? So that's why it is usually the case that a continuous distribution give you any number, the probability that equal to that exact number exactly will be 0, right? Because if not 0, then you add something infinite, right? Then the probability will explode, right? It's because it probably must be between 0 to 1, right? So that's why probably equal to a particular number, that will be 0. So the px is always 0. Okay, so that's why we don't talk about this. Is not we can't define. We can define it. It's always 0. So what's the point of talking about those? So instead of talking a number, it's only meaningful to talk about an interval, right? And that will be meaningful. So that's why we talk about f. F is meaningful because f will be non-zero. Okay, for some meaning, I mean, if most of them is meaningful, right? And when you have the f, we can also define something called small f, and that is meaningful thing because although by itself doesn't mean anything, but it can tell us the area under this small f curve is the probability. Okay, just to quickly remind you this because I think it's very important. I just spend one more minute on this one. So is in the continuous case, okay, suppose we have a f here and small f here, right? And f sometimes look like this, okay, and f will be something look like this, okay. And the first thing you can see, if x is big enough, then it will be close to 1, because f of x is talking about the probability that x less than or equal to x, right? So when x is very big, right, this one go to 1, right? When x is big, right, and x is large, right? Because it's asking what's already less than or equal to that. When x is very big, then this must be go to 1, right? And second thing, that of course this is small, they go to 0, right? I'm not going to mention it. When x is very small, then it's 0, right? If you really want to say, I'll say it here, right? This guy, right, or this is f of x, right, will go to 0 if x is very small. Okay. So that's why it always come from small to big, right? Maybe I just change color to make sure it's more, right? Something like that. Okay, it must be increasing, right? That's cannot decrease, right? Must increasing. But anyways, you don't need to know this, but the main thing is is the following, right? Say this, say suppose I pick up any arbitrary point here, right? This is A, this is f of A, right? This is the probability that x less than or equal to A, right? So in this, you need to know is this A is here. It is asking this probability. I don't know. Maybe I go down. Okay. Then this height is exactly this area. If we take this area will be P of x less than or equal to A, and this is f of A. Okay. So this is the main thing you need to remember in your mind, and we'll be using it all the time. And the area under the f, the small f curve, must be 1. Okay. So that means that the orange one, okay, will be 1 minus FA. Okay. This is equal to the probability x greater than A, or greater than equal to, doesn't really matter. This one doesn't, whether you add equal to doesn't really matter. Okay, because when continuous equal to that one particular number is 0. So it doesn't really matter whether you add A or not. But this is the main thing you need to remember, and this distinguishes the discrete version. Okay. I hope I think I talked about this for 3 times. I think hopefully it's clear. And this is something you need to remember in your mind. And because otherwise you don't know what's going on. Okay. I hope that is clear. I mean, everything is in the notes already, but I just want to emphasize this thing, and then you will understand what's going on. And and with expectation and variance, although we because of continuous, we can't really write in discrete way. Okay, so so that's why we need to talk about things a little bit more trickier. We need integration, but you probably need not worry about the expression, but rather you know intuitively what they mean, right? It still means the same. If you repeat the experiment many times, every time you convert the outcome to random variable, right? And you record those numbers, you calculate the mean, it's expectation. Calculate variance, is the variance. Okay, so that's nothing new there, same as discrete. So everything is same. Okay, and that's the thing you need to know. And why you need integration, or how you calculate. If you are doing accountant or accountancy, or you're doing something not related to finance, probably it's okay. Okay, if you are doing quantitative finance, then you should know it. Okay, you should also read the proof if you are doing that, because I mean, most of you are not doing the second course in your statistics, so it shouldn't be matter. Unless you're doing further, then you need to know those. Okay, I mean, after that, you will come back to this slide or come back to this and you see what happened. Okay. But it's not important for the moment and important for our class. Okay. So last time this is 5 or 6 common continuous distribution. We'll finish all of them today. And so I don't think you need to worry about it because we cover everything there almost, right? Uniform we cover already, right? And you ask what is the use of uniform, right? Uniform is saying that you don't really know, right? You know the number is between some interval. You actually don't know which one is more likely, then you just assign uniform. And uniform is usually the best way if you don't have any knowledge about those. And then how you apply further, right, is you learn the base rule. Although we don't tell you how to update with continuous random variable, but the idea is the same. You keep updating and learning, and then you will learn the real thing that would be useful. And that is what people start with the uniform, right? And exponential, we learn how we can use it, right? Is the idea that you try to model the arrival time for certain event, right? Remember how we define exponential? I think go to slide will be better. Let me go to slide, it's easier, right? For uniform, you don't need to remember. I don't think you need to remember the formula, right? You can forget, simply just know how to do calculation by the example, right? But with this formula you'll be using, you can forget about integration. And you also probably want to know the mean and variance, but probably you don't need to remember because you just apply them directly. I think the key is look at the exponential because this is something that you notice that is you cannot use the bell curve. Okay, most of the time you can use bell curve to solve most of the problem, but exponential you would probably want to model the time. Probably you don't want to use bell curve. The reason is being that look at the exponential, the support is being from 0 to infinity, right? The time until something happens is always a non-negative number. But when we use normal come from negative infinity to positive infinity, right? So doing the time would not be put it in is not appropriate, right? And this is something rather simple. It's just like how long you need to wait until a success. You assume the process is Poisson with mean lambda, right? That's basically you say you are thinking about something arrive, right? And you just have the main thing is memoryless, right? It doesn't really matter, just to remind you what is this is, it doesn't really matter how long you wait, okay? It is the same. What does that mean is, you mean that you think something arrive in the next half an hour with probability, say 1/2, okay? And after you wait 15 minutes, if it doesn't arrive, you mean the same. The thing arrive in half an hour, still 1/2. No matter how long you wait, you still believe the same. Okay? You have a constant, strong belief that things arrive in the next half an hour, always the same. Okay? You're adamant about that, right? So this happened. You may think it's weird, but this actually happened. Look at the old fog log story, right? There's a mountain here, there's a seaside here, right? And the old story is the house there, there's a woman, okay? And she's waiting her husband to come back, right? Every day he goes out and look, and every time he will say, my husband is going to come back, right? Every day until she dies, right? And eventually she becomes a stone, right? Standing there, right? I think that someone have heard this story, right? This like M.Phil said. So that is keep looking at his husband to come back, right? All the time. I mean, you can change to the guy waiting for his wife to come back the same. And there are many stories around the world. I mean, that's become a stone, right? And the same, right? Because no matter which day, I mean, no matter how old it is, how many days has been passed, the same happens, right? It doesn't change. Okay. So that is the story here. Because why I talk about this story is important because you can prove, but we don't put it here, is if you want to model the arrival of event that has this property memoryless, there's no choice but exponential. Okay, we don't prove it, but that is the thing you would lose is if you believe the process memoryless, there's nothing but exponential. Okay, so there's no other choice. But compared to other things, you can consider sampling, you can do hypergeometry, you can do binomial, many things. But if you believe that this is memoryless time property, yeah, that is exponential. You cannot use uniform, you cannot use other. And the thing you need to remember, I mean, you take care not about the F, but about the F, right? It's something we often use, right? This is the formula that you'll be used to calculate. And I want to emphasize later today, we will do Excel. So this formula probably in the real practice, you don't really need to remember, right? But the computer, you just tell them the lambda, tell the X that will give you, okay? But just let you know what we are doing here, okay? And just to remind you why we have mean and variance here, okay? Just to remind again, right? Because suppose in the Poisson process, okay? The Poisson distribution, you say you expect in an hour that 2 events happen, right? So Poisson, consider the case you have a Poisson with mean 2, okay? So it means that in an hour of time, 1 hour, okay? You expect on average that with 2 events comes out, but that means lambda is 2, right? So you don't know when, but just like in an hour, you have 2 events happen, right? So that means what? It means that the first event when it comes out, okay? You expect that the event will comes out in the 30 minutes time, right? So the first event comes out and the second event comes out, okay? So that's why it means that 1/2, right? Hour is 30 minutes, right? So the first event comes out is 30 minutes, so exactly 1 over lambda. Okay, that is what it means by 1 over lambda. Because if 2 events comes out in an hour, the time it happened, right? The first event comes out is 30 minutes, right? Every 30 minutes you have an event. Remember memoryless, right? So we just need to you just need to model the first arrival of the first thing, right? Because every other thing is independent if it hadn't happened, right? Is that clear? So although we just model the arrival of the first event, you don't need to worry about the subsequent event, right? Because after the thing happened, everything restart, right? Or don't even that. I mean, even you just wait the thing happen, then everything restart. So that is what it is. Is that clear? What's going on here? Okay. So just to remind you that everything the whole class is a record. So that's why in case you miss anything, just go back to check the video again. You can take the screenshot. So if I'm too fast to cut it out, then you just go back there to check out. Any question? This has been covered last class already, so I just try to be brief. Okay. But I think it's important, so that's why I just talk again a little bit. So the bell curve. So today the focus is bell curve, because later all the other things is just a continuation of bell curve. Okay. And this is so important, so please pay attention because we'll be using it for the rest of our course. Okay. So the bell curve, probably you remember this all the funny expression, okay? And they are not important for our purpose, okay? And to be honest, I can't remember. You just asked me, okay? On the corridor, what is normal F and big F? I can't write it down. I mean, if I'm not teaching, you ask me, say after the Christmas break, ask me again, I can't write it down. I mean, there's no need to remember that, okay? As long as you know this is a bell curve, then it's fine, okay? If you see this is a bell curve style, then it's fine. You need to remember. But the important thing is it can be used a lot of scenario, right? Just to remind you why this is important. And the first thing is you come empirical thing is look at IQ, EQ, weight, height, and many things. It's just follow this normal. The reason why this is later we will see is coming from what we call a central limit theorem, which comes from the central limit theorem, which we will learn, I think, next week or the week after, which essentially said, loosely speaking, is if a measurement, okay, actually is coming from many factors, okay, the measurement is affected by many factors, okay, and it generally you will lead to normal, a bell curve, okay. If it affected by so many factors affecting the same thing, then it becomes normal. And you can see that's happened with IQ, right? IQ depends on your dad, your mom genetics, DNA, and your parents, great-parents, so on and so forth. And also what kind of food you eat every day, what kind of drink you do, what is your habit, all of the things are contributing to your weight, your height, your IQ, right? All these things. So that end up is being a normal, okay? And you probably ask why we need to learn normal. It's because of the fact that when we do sampling, okay, and the sample mean is indeed coming from many small things add up together, right? Because when you draw one item from the population, okay, and you keep drawing this and you get an average of those, right? Then that thing as a normal. Okay, we'll talk about that soon, but the week after. So that is the reason why we keep learning normal, because this is actually when we draw samples from population, the sample mean actually follow a normal. So that's why normal is very useful for the rest of the class. So basically you will see normal for the whole course after this class. Okay, we'll be doing all the time like this and make all the assumptions based on normal. Okay, that is the reason. I mean, of course, we will elaborate more, but that is the idea of the basically whole class, and same as whole course. Sorry, the whole course. Okay, and I think just go back to this graph is important. Is the thing you need to remember from this is normal. You have two things: is mu and sigma square. That's important. And mu control the mean, sigma square control the variance. Okay. The key thing here is look, compare this to the before is they are separate. Okay. You increase the mu has no impact on sigma. You change sigma has no impact on mu. Okay. So this is different from, just go back to go to this slide. This is different from all other distribution, right? Remember Poisson, right? If you change the lambda, you change mean and the mean and variance. Same for the other thing, right? Just like you change one thing, you change the other. But for normal, they're separated. Okay, you separate it. So if you change mu, you just shift left or right. Compare the blue and the green. You just change the mu, just shift left or right. If you change sigma, compare the red and the green. You just spread out differently, right? Just to remember the metaphor. If a dove there, use a hammer to hit, right? If you increase the sigma, you just keep hitting it, it just spread out. Okay. So that is the main idea behind this too. Okay, the mean and the variance. Okay, and this is the shorthand notation we use throughout the class. Is because it's so commonly used, normal. That's why we will have a snake. Okay, X is distributed with normal, with mean mu, and variance sigma square. So this is the notation we're using, and this is actually common notation for statistics, but we just introduced here because we usually only use normal. Okay, later you will see we also use T other thing as well, but we just need this notation. Okay, and here is important thing. Okay, is the following. So if X has a normal distribution, okay, and you multiply by A times B, it is still a normal. Okay, so this is a very important features of the, or also a very useful property for normal is you add and subtract, you multiply. Actually, will the bell shape is still a bell. Okay, The only difference is, only thing is you change to the mean and variance. Okay, so but this is the mean and variance comes from what you learned before, right? So expected AX plus B is A expected X plus B. So that's how you get this guy, because expected X is mu, right? This is mu. That's how you get this one. This is a mean. And the other one is coming from the variance of AX plus B, right? It's coming from A square variance of X, right? And this guy is sigma square. Okay. So this is coming from these two formula that we have learned earlier. Okay. And this is only important, okay, because we have the following formula. Is that okay for this formula? Because important thing comes from the next formula is whenever we have any normal random variable, we calculate the standardized version, which is subtract its mean and over its SD, we give 0.1. Okay, look, go back to here. If A, okay, what we have is here, we subtract the B, so B is negative. So you can see how we subtract this, right? We subtract the mu, that become 0, right? And we over the sigma, you become 1. Okay. So why we want to do that? So the main idea what we are doing is the following. Okay. Let me show you the idea what we are doing. Okay. So the main thing is I have a bell curve. Okay. This bell curve has a normal. Okay. This guy, we have X, right? X like this. Okay. So what actually we are doing is we are transforming to a Z, okay, which is also a bell curve, okay. And just to remind you, this is mu here, okay. And we basically transform it to 0 here, right? Z is normal 0, 1, okay. And the reason why we are doing all this thing here is because of, suppose we want to know, I know this is called A, I guess, okay. I want to know the probability of this, right? I want to know probability that X is less than or equal to A, okay. So remember how we do this, this is F of A, right? And how do we calculate, right? You have to put it in the crazy expression, right? And I told you already, this crazy expression, you can't use the hand to calculate, right? You have to use computer because the integration by itself is not computable. There's no closed form solution. Okay. So then the calculation will be complicated, right? Because you, in the old days, right, you need to go to the computer and check, right? There's no computer, right? There's no computer. So that's why it's very difficult to do, right? Because if you every time you need to compute, then it's very complicated. Okay. It's better to have a table, right? To tell me, okay, under this mu, under this sigma, okay, for whatever A, you give me the number, right? So let me repeat the statement, right? You don't want to compute all the time, right? So in the old day, what do you do, right? For each mu and sigma, I have a table of F, right? So what I mean is, say, I have a number X, right? And F of X, right? You tell me -3, -3.1, -3.2, right? I have to calculate all this here, right? Look at the table. I do the calculation first, and then every time I need to check, right? I don't need to redo the calculation again, right? Because it can't be calculated, right? But I need to prepare this table, right? For every mu and sigma, right? Then that means I need to have so many tables, right? Because there's so many combinations of mu and sigma. So here, that's why things come handy, because I can transform this into here. Okay, I can transform this is A minus mu over sigma, okay? And this area and this area the same. So I just need to find this guy. Z is less than A minus mu over sigma. Okay, so that is the main thing why we're doing about this is in that case, I just need to prepare one table, Z, okay? And I give -3, -3.1, and so on and so forth, right? And power f of Z, okay? And that make our life easier, okay? We don't need to compute and all the combination of mu and sigma square, but instead I just need single table. So that's why this is called standard normal, okay? Has a normal with mean mu and variance 1, okay? And of course, if computer, you may ask, okay, do we really need this? And still actually you do. Even the computer is just storing these numbers and just put there, okay? It's much faster to do in this way. And okay, so later you will see, actually you will do, don't worry, this graph will be seeing this throughout the course. Okay, again, as I remember, as I told you that don't worry about this is, I keep drawing this graph, I think for the rest of the semester. So don't worry. But this one you must sure you understand. I think I draw this many times already last year. I think this year I keep drawing it again. Okay, so now that I mean the Z table, okay, is one thing is like you will be, this table will give you this the f of Z, okay, and here in the table usually you are given only is Z is negative, okay. So basically what usually the table would give you the following is about here, because standardized is a 0, right? So basically it's asking, this is negative, right? So basically give this number Z, maybe I use other color, blue, darker blue, okay? This area, okay? This is what this number is, okay? Usually this is the table they give you, right? And the reason why they don't give you anything positive is because they are symmetric. Suppose you want to find something like, say I want to find this guy, for example. I want to find 4, okay? What is this guy? Okay, what is this guy? Suppose I want to find this guy. What is probability less than 4? So what we're going to do is, because of symmetry, okay, probability of, okay, less than 4, okay, is same as probability of Z is more than -4, because symmetry. The reason is being, look at this one. You just flip it, -4. Look at this area, they're the same, right? So less than 4 is same as greater than -4, right? And more than -4 is 1 minus less than equal to -4, which this guy you have from the table. Okay, I mean, don't worry, we'll do example, but this is what it means about the Z. Okay, the reason is F is symmetric, because normal the bell is symmetric about 0. Okay, so don't worry, we were doing more exercise to show you this is correct. Okay, so this is something that you'll be doing for the rest of the course, so that's, don't worry. Okay, now let's see the example. Probably I'll show you the table because I think that would be important. So let's see. I think I just look at the Z table. Okay, go to the, so actually you can see there are many things you can find, but say this is the Z table. So this is exactly what's going on here. So settable.net. So this, as I said, right? You have a negative C, this is a value. And this table gives you how to read them. For example, this is 0. I don't know whether you can see it clearly. So this number tells you less than 0 is half, right? And you have to add this guy. So this is 0.01, sorry, negative 0.01, okay? Because everything is negative, okay? So that's how you have the Z table, okay? And you need to know how to do this because in our final test, you cannot bring your computer, okay? So you have to print the table you like to the venue. I don't print that for you. You can bring your own version. The reason why I don't print it out because everyone has their own favorite. Some people like to read the positive, some people like to read the negative. You decide what table you want to bring, okay? It's an unlimited number of pages you can bring, okay? So that's the C table, or you can look at this one, they give you the positive one, okay? But I think there's no difference for us because you know they're symmetric, okay? So sometimes they give the table, they give table, this is the one, they give the left one. Sometimes they give the positive one, okay? But they're symmetric, they're the same, okay? You give it positive, you give me negative, the same thing, okay? Because this one, you -1 is the right tail, right? Same as the left tail thing, okay? So in the exam, you bring what you like, okay? So for this one, let me show you how we can look at this number, okay? A Z table less than 1.4, okay? So let's see here, okay? Let's use this one because this is exactly what we want, okay? And less than 1.4, actually we don't because we need to rely on this thing. So let's see how we do that. Is it all? Someone asked me a question. Is it possible to bring the notes? Yeah, you can bring whatever non-electronic to the venue. Okay. So let me finish this example, then we'll break. Okay. So the question is, the first one is the following. Okay. This is 0. This is 1.4. Okay. So the question is, this question is less than 1.4. So just this area. Okay. So what are we going to do? Okay, is you just flip it. Okay. This is same as negative 1.4 here. Same blue. Why this is true? Because symmetric, right? This is same regardless you look from the right hand side or left hand side, right? And remember, table we look at can give us this area. Okay, we look at this area and we do the subtraction, then we're done. Okay, look at negative 1.4 to the left hand side and subtract from 1, then we're done. Okay, is that okay what we're doing? Okay, so let's see how we do that. Let's look at the table. Okay, and negative 1.400. So this, we look at the first column. Okay, look at 1.4 is 0.808. Can you see that? It's this guy. Okay, can you see that? 0.808. Okay, so go back to here. Okay, the table tells us this guy is 0.0808. Okay, so what's blue? Use our kindergarten knowledge. The area is 1, so this guy is 1 minus 0.0808. So that is 9192. Is that clear? Don't worry, we'll be using it all the time for your course. So we will be doing that all the time. Is that clear? Okay. And later, actually, you see, if you use Excel, then immediately you know this is the answer. Okay, but suppose with the table, this is what we do. Okay, just go today. Probably one of the homework you may want to do is find out the nice set table you like. You want to bring it to the test. Okay, because but you don't need to hurry. You still have 2 months to go. Okay, to pick up the. So the next question is less than 1.6. Okay, so that's easy because actually it just asked the question, right? This is 0, negative 1.6, just this area, and just directly looking up, right? The table we have is exactly what we want. Is this guy 0.0, this guy 0.0548. Can you see that? Okay, so that is the number. Okay, and probably you want to ask, okay, why I calculate this guy? Because sometimes you have this table. Okay, the table is not this one, but this guy. Okay, if this guy, then you have to look at net 1.6 and subtract. So that's why you have 0.9452 here. Okay, depends on really which graph you're looking at. Okay, here in this table I look at the positive z, but anyway, they're the same thing. Is that okay? Is that okay? So lastly, I want to show how to calculate this too. Okay, less than 1.6 and 1.4. Someone asked me, can you bring anything? Yeah, you can bring anything as long as it's not pornographic, not something you can bring, then you can bring. Okay. Okay. I mean, cannot be any obscene, pornographic, anything criminal, then you can't bring, then you can't bring, right? So there's no limit you can bring. The 0, okay? This is 1.4, and this is negative 1.6, okay? So this is the question here, okay? The blue one is the thing they ask, okay? And how to do the calculation, okay? The thing is, we can calculate the orange or the red one, which has been done in the second one. Okay, this is the second one. Okay. And also we have an green one. Maybe this way. The green one, which come from the first guy. Okay. So again, use our kindergarten math. Green subtract from orange is blue. Okay. So basically you subtract the first line to the second line, then you get the last one. Okay. So we will be using this throughout the course. Okay. So during the break, if you have problem looking at this, then please let me know. I'll try to help you out, but let's a break of 10 minutes. We resume at 1:30. I go around to check out if you have any question. The easiest way is when they want to know. Because either you like it, you can cover it and you have to So there's some question on the so let's resume. There's a question asking whether we have quiz. The current progress of our, we're slightly below our schedule. So only if you have enough time, we will do a quiz. Otherwise, we don't. Okay, and we will decide if we don't have time. So how to make up the 10%, or we just keep it for free. But otherwise, we'll decide what to do. I mean, if we have enough time, then we may give a quiz at the end. But otherwise, I guess most of the time we don't have time because we have too many things to cover. So based on last year experience, I don't think we have time for this. So we'll consider maybe some alternative assignment or just keep it for free, depends on scenario. Okay. But so don't worry, I will not do any surprise quiz or whatever. If I do have an answer in advance, you will know it. But so far, I don't see the possibility that we have there. So you can safely ignore those. Okay. So just during the break, someone asked me the test thing, right? So it's a 1 hour one, it's open book, so you can bring whatever you like as long as there's no internet connection. And someone asked me what kind of calculator you can bring. Whatever calculator that has no internet connection is fine with me. Okay. But because iPad has internet connection, so I can't allow that. I mean, anything with Bluetooth connection or internet connection, I can't allow that to be there. Okay, because of possible cheating. Otherwise, you can bring whatever you like. Okay, so bring your handout, bring your notes, bring your cheat sheet, whatever. I don't really care. Okay. So let's finish this. Okay. So probably many of you might have know what we call the empirical rule or rule of thumb. They call the 3 sigma rule or 68, 95, 99 rule. So if you try to look at that, I mean, that's a very famous. Okay. So what does that mean? It just means the following. Just let me draw here because there's enough more space. It just means the following. Oh, so this guy. Sorry. I always didn't draw very well. I'm sorry. Okay. Although I have a PhD degree, but my drawing remains kindergarten. But I hope you're okay with that. So this is the mu. So what happened is this is the following. Okay. So what it said is, if you look at this, mu plus sigma, mu minus sigma, this area is 68. Okay, or 68%. Okay, or 0.68. Okay, or what it means is probability that x is between mu plus sigma, mu minus sigma is 0.68. Okay, what it means is like, roughly speaking, it's like 70% of the thing is within 1 SD, right? So that is what it means. Okay, and the next thing will mean by simple expression, you know, mu plus 2 sigma, mu minus 2 sigma, right? This area is 95, okay, or 0.95, okay. So basically, you can safely say most of the things actually fall within 2 SD, right? So that's why usually we have the 2 SD rule, okay. So so if you, as I said, right, a lot of things basically normal. right? So if I tell you the mean to the SD, basically you know pretty much most of things should fall within 2 SD, right? And 3 SD is 1997, 99, right? So basically that is what it means. Okay, that is a 3 sigma rule, and that basically 3 sigma is enough for most purpose, right? For planning or for prediction. So that would be the thing we're using. So probably you should remember. Probably you remember. We do many math in this class. The calculation. The 2 SD rule. Okay. Within most of the thing within the 2 SD will be the thing we'll be using throughout our course. Okay. Of course, we'll do exact calculation, but this is the rule of thumb is so useful. Okay. Then actually ask you to probably this is an important question we'll be asking is suppose you do a midterm, not our class because our class is not a midterm, but you do a midterm for the other class. Okay. The teacher told you the mean of the exam, mean of the midterm is like 80, right? And they tell you the SD like say 5. Okay. So you may ask yourself, should be the right sample should be S, right? So the question would be, okay, if you are getting 90, right? 90, how well you're doing, okay? If you're in 90, then probably you get an A for almost sure, right? Because very few people are more than you, right? So if you're doing 85, are you good? Yeah, still good. Is you are above the 7%, right? So probably you should get a B plus, right? If you get a 80, then it's mean. Then depend on how symmetry or not. But if you get 70, okay, it's just 2 SD below the mean, then probably you are not doing very well. Okay, probably if you work very hard, then you still get a B minus or depends, right? And but that would tell you what does that mean. I mean, if you keep this performance in the final, then that's what you see. Okay, so even though you don't know the distribution, the teacher doesn't tell you, and you can usually safe assume normal would be a good approximation. Okay, so that is the 3 sigma rule. Okay, I hope that's clear. Is that okay? So this is 3 sigma rule, and probably if you learn management, you will know this is something very important, right? Because this is how you evaluate the performance of a certain thing, whether they're above or below, right? Because normal is something that you would expect to be. Okay. So now the next thing is we often use normal. So one thing probably we would asking the question is we reverse what we're asking. Okay. So what I'm talking about here is before we just say probability that X less than A, I give you A, you calculate the number here. Okay. What is this guy? Okay. So what is this? Is right? This, right? I give this. I have a mu. I have an A here. Ask the A, right? Then we told you that you can transform this to Z, right? Maybe I do look at Z first. I mean, that is easier. The Z, okay. And that would be the idea what we're doing, right? And now we ask another question, okay? And this is what we're asking, right? The question is reverse. Inverse normal means I have this guy, I give you this. I give A, you give me go back. So what it means is I want to know the following, okay? Which often appear is I give you this area, okay? This area is called A. I want to figure out this guy. That's called C of A, or maybe I call it alpha to be same as your slide. That's called Z alpha. Okay. I give the probability, which is alpha between 0 to 1. I want to ask what's the number such that in the normal, right? Standard normal, what is the number? What is this number such that it's less than that number is equal to alpha? Okay, just reverse. Okay, so probably you will see this as a very technical thing, and when you look at the table, you do it reversely. But this is the thing that we keep using. Okay, we'll be using this for the rest of our course. Okay, so later you will see why we are using it. Okay, but let's see the example, and you will see it's not very complicated because you just reverse what we are doing. Okay, so this is the way we define Z alpha. Okay, because of symmetry, so you define it to the left-hand side, same as the right-hand side here. So the one I just drawn is remember the one I drawn is this guy, right? I drawn alpha is here, okay, and they're the same, okay, because look at alpha is here, okay, this is called Z alpha, and the way we define is negative Z alpha, assuming Z alpha is positive because they are symmetric, okay. So I just terminology is like this, okay, and why like this? Because the textbook, many textbooks follow this terminology, so I used it this way, okay. So Z alpha is a positive number, just let you know. But anyway, we just trying to do this, okay, very often. Is the question, what is Z less than Z? Is 0.95, okay. So this is something we often do, okay. So how do we, what is it asking? Is this question, okay. Let's draw it because I said I keep drawing this graph. I hope after many years of drawing I can improve, but you can tell me still a kindergarten thing. So what is here is I want this area, okay, is 0.95. This is Z. Okay. I want to figure this out. I want this is 0.95. Okay. I want to know what is this number. Okay. So it depends on what table you're looking at, right? And 0.95, right, must be, when you draw this, must be beyond 0 because left of 0 is 0.5, right? So it must be on the right-hand side of 0, right? On the left-hand side is less than 0.5 because symmetric, right? The total area is 1. So this is on the right-hand side. So that's how I draw this graph. And when this is 0.95, so this guy is 0.05, right? So you can similarly look at this idea the same. Is to look at this. 0 is here. Some negative Z here. This guy is 0.05. Okay. So what we are trying to do is look at the table that give us the negative value with 0.05. Okay, 0.05. Okay. So let's see. Let's look at the table we use. Let's use the first one first. Okay. We're looking at the area entry. The area is 0.05. Okay. 0.05. Look around 0.05, 0.05, 0.2. Okay. This is a little bit too small. Okay. Somewhere between these two, negative 1.6, and between the fourth and the fifth column. So it's 4.5 and 4.04 and 0.05. So 1.645. Okay, because between these two columns. So that is how we get this guy. Is that clear how we get this one? Okay, so let me do it again. I guess that would be important. Okay, so the left-hand side I need 0.05. Okay, so what I'm going to do is instead of looking at the column and the row, look at the entry, which is 0.05. Okay, and I don't know whether you can see it clearly. Okay, and this is just between this will be this one. okay? Because this is in between is -1.6 and this 2 column, okay? Okay, so that is how you get it, okay? So I don't know which kind of table you like, but you should make sure that when you go to your final test, you know which table you're looking for, okay? You bring your own table and then make sure that you know how to work with your own table, okay? Or if you have another table, that will be easier. So in case of the table that I show another one, this table, okay? If the table is like this, then it's easier because this already is the area. So we just look at 0.95 in this table, okay? Because this table is already exactly what we want, right? It's exactly this table. So this table, I just look at 0.95. So exactly this 2 guy. I don't know whether you can see clearly. Will be this guy. Okay, because this is 0.9495, and that is 0.505. So it's 1.6. And okay, so this is 1.6 here. Okay, and it's between 0.4 and 0.5. So that's how you take the middle one. So it's 1.65. Is that okay? You can pick up whatever thing you do, then it will work. Okay. So you may want to bring this. Actually, you may want to bring the 2 table, right? Because the 2 table is enough for all the purpose. Okay. I mean, probably you would not feel easy, but don't worry, you will be using it for the rest of the course. So it's hard not to know, okay, if you attend the class. Okay. So the next one is asking, I will do it again because I think that would be important. The question is, okay, what is the probability that Z bigger than Z is a very small number, okay? Then it must be the case is beyond on the right-hand side of 0. The reason is being that on the right-hand side of 0 is already 0.5, right? So you must way above 0, okay? Because we want this area to be very small. It's 0.025, okay? And there are 2 ways to do it, right? The first way is to go look at the symmetric case, go back to the idea, suppose this is Z, right? And we go back to here, is negative Z, is this area is 0.025, okay? So we look at the table, look at which entry is 0.025, then we're done, right? So look at the table. We try to look at the first table here, okay? We look at this entry, look at here, we look at 0.025, okay? So let's check out which is closer, 0.025, 0.01, 0.02, 0.025 is somewhere here, exactly 1.96. So I don't know whether you can see clearly. This is 0.025, okay? And this is negative 1.9, and this is 0.6. So it's negative 1.96. Is that clear? I hope you know how to do it. You can pick up whatever set table you want. I think it's fine. Okay. And the other table you want to look at, the other way to look at this is look at the other way around, look directly, because what you can do is look at this guy. Okay. Okay. Now remember, this is negative 1.96, so Z is 1.96. Okay, just make sure that you don't confuse with the negative sign. Okay, and the other one, this is 0.025, so this is 0.975 because they must add up to 1. Okay, so you can look at the second table that gives you 0.975. Okay, and so probably some of you may have query in your head that which table you should use. Actually, later probably next class, probably today, not enough time. You can use Excel, create your own table pretty quickly, easily. Okay, you should be able to do that very quickly by yourself. Okay, you don't have to follow the table. Okay, so again, 0.975 is here. I don't know whether you can spot it out, but I can spot that quickly. Here is 0.975. It's 1.9. Okay, and then you go up and then see is 0.0, 1, 2, 3, 4, 5, 6. So that's why it's 1.96. Okay, so this is how you check it out. Okay, so make sure that you know how to do it, because we will be keep doing this for the rest of the course. If you don't know, then you lose it. Okay, but of course in the class I will show you how to do Excel. I'll keep doing the Excel thing, but you should know how to do a table form, because you don't have access to the table. Don't Excel in your exam. Okay, so I think I pretty much do everything here. So let me go to the other one. Okay, so this is the question I mentioned in the beginning. Is usually what you have is not the Z, it's not the standardized normal, but you have it like this, right? So I have a normal with mean 20 and sigma 16, right? So you can imagine that this is exactly the test result, right? Midterm test, right? Have mean of 20 and variance of 16. So the sigma is 4 here. Sigma is 4. Okay. So the question is asking, okay, what is the probability less than 16? Okay. So that is the question. So basically asking you what's probability be 1 SD standard deviation below the mean, right? So x minus 16. Okay. So the thing you do is you need to convert this to what we call standardized normal. Okay. So how do we do that? Is you subtract the mean mu, okay, over the sigma, okay, then itself actually becomes Z. Okay. So that's why it's 16 minus 20 over 4. So give you -1. So what you're going to do is looking at this table, right? This is a Z. Okay. This is 0. This is -1. We're looking at this area. Okay. The thing is, why what we're doing is what we're asking, we're looking at this one. X 20 here is 16. Okay. And these two areas the same thing. Okay. They're the same area. Okay. So that is what we're trying to do. Is that clear what we're doing? Okay. I'll show you again how to look at the table once more. I'm not going to keep doing that. Okay. Look at table -1. How can we do that? Okay. Look at the table here. Okay, this one. I look at this one easier because -1, right? So -1, we'll be just looking at the row, which is -1 is this guy. Okay. 0.1587. So this is, I don't know whether you can see it clearly from the back, but this is how we look at this. Okay. So that's how you get this guy. Is that clear? I mean, very soon you will use Excel to calculate, of course, and you will see very fast. Okay. So the next question is the following, right? The question is greater than 24. So what the question is, X, okay, normal with mean 20, okay, asking 24 here. Actually, again, 1 SD. Okay. Actually, without calculation, you should know they're the same, right? Because it's left and right. Okay. But let's actually check this out. Okay. This area we want to know. Okay. So how do we do about that? Is we have a Z here. Okay. Still a bell curve. This is 0. And what's this guy? Is actually 1. Okay. Because actually this is a 24 compared to 20 is 1 SD, right? So that's how you do it, right? You minus the mean, right? And divided by SD, right? This 24, how to get this guy? It's 24 minus 20 over 4, Okay. And the blue area, the same area. Okay. And since this is positive, let me use the second set of the graph, maybe easier, right? Look at, that doesn't really matter. I don't know which one is easier. Okay. You can use this, I don't know whether you want to do it, but you can figure out the orange color, okay, directly and take one minus. Okay. So as you can see here, the orange color will give you 0.8413. So let's try to convince you this is the case. Okay. Now go to here. Okay. As I said, I look at the look at this one, right? Look at this one. Okay. Look at this table. Look at the number one. Okay. It's actually here. It's 0.8413. Okay. I don't know whether you can see that clearly, but this is the entry, right? So the orange one, right, is 0.8413. Okay. So I hope that is more or less clear. Okay. So that's how you get it. Subtract is 0.1587. Okay. Don't worry, as I said, we'll be doing this all the time. So you will know it. Okay. And also your assignment, so you make sure that you will know it. Okay. Any question? We'll talk about Excel next class, so you will see again how we do it. Okay. You can construct your own table. Okay. Using Excel fund, you should know how to construct. You can create the table that you have seen. You can create this table by yourself. Okay. You can create this quickly. Just Excel entry, then you're done. Okay. Just several. You can create it within one minute, less than 1 minute. Okay. Okay. If no question, then let's continue. Okay. Now the next one, I think this is the most common one. Again, let me talk about this. Okay. So the question is asking X, maybe, or here. Okay. X, L shape here. The mean is 20, right? So the asking is between 16, maybe black color, can't see, right? 16 and 24, okay? What is this probability? Okay. And what we're going to do is to transform this guy to a Z thing, okay? Again, this becomes a bell, this becomes 0. And actually, you know this is -1 and 1. Okay, how you transform? 24 minus 20 divided by 4. Okay, same for this guy. Okay, 16 minus 20 divided by 4. Okay, so these two areas are the same. Okay, they're the same. Okay, and in math, it just use same as what you do, right? They subtract this guy, right? And you get -1 and 1. Okay. And how do you solve this, right? It's the same idea you do the kindergarten, right? So you calculate the orange area, okay, and subtract it from the green area, then you are done, right? And the orange area actually we calculate less than 1 is 0.8413, and the green area is 0.1587. So get the answer is 0.6. Okay, so that actually is the number that you remember the empirical rule, right? 68% is between 1 SD, right? Actually, this is what we have the question. So not minus. Oh, okay. Someone, yes, there's a typo here. Probably, I think it's right. Is it negative? Yes. Yes. Yeah. Thanks for reminding me. There's a typo there, but right. The green one is the less than -1. Okay. It's the orange minus the green give you the blue. Maybe I should use blue to make sure that it's perfectly clear what we are going on here. Okay. So is that clear what we're doing? Okay, we'll be using this all the time. Okay, so make sure that you fully follow and you know how to do it. For if not, then you may be confused in the upcoming classes. Okay. Okay. Any question? Okay, I think it's enough. So let's continue very quickly. Okay. So here are some property. Okay. And we don't prove it, but I think it's easy to see why they're true. Okay. And that is something very interesting thing about the bell curve is if we have one bell curve from X, another bell curve from Y, okay? Turns out if you add them together, okay, it is still a bell curve, okay? So this is not always the same. If you add two Poisson, it's not Poisson. If you add two exponential, not two exponential. But for the bell, it's very special case. You add two bell, it's still a bell, okay? And you just add the two together, the mean and the variance, which you know very well. Why? Because expected X plus Y is expected X plus expected Y, right? You learned that, okay? And we also learned if they are independent, right? Variance of X plus Y is variance X plus variance of Y, okay? So that is true when they're independent, right? So that is the same idea here, right? So I hope that is clear because we'll be using this in the later stage of our model because we keep using this adding the normal, okay, sum of the normal. And we also will talk about things like difference between the bell curve, okay? The interesting again is only true for normal, okay? Not true for anything else, okay? Blue minus the red one, okay? Interestingly, the two bell difference is still a normal, okay? So this is super surprising, but we don't prove it, okay? Because the proof involves very complicated calculation, which we don't want to go about it. But the thing is, the two bell add together is still a bell. Subtract the bell is still a bell. So that is something you can, as a shorthand to remember. Okay, bell combined to bell is a bell. Okay, and the mean is just take a difference. This follow from this guy. Okay, and the variance follow from this one. Same idea. Okay, so graphically, what does that mean? Is the following. Okay, just quickly to draw the interpretation is the following. Suppose I have a number line here, right? What's going on here is the following. I have a, again, the blue one, a bell curve here, right? And I have another bell curve here, okay? What it means is, I call this X, right? And this is Y, they're all bell curve. And I add them up, okay? Z is X plus Y, it's still a bell curve, okay? So two bell add together is still a bell. Okay, so of course it should be more spread out, but I mean, you know what do you mean by that? Okay, because the variance is much larger. I should be, maybe you want, I should be a little bit more careful if I want to draw this guy. Okay, this will be, the mean will be mu of X plus mu of Y, right? If you want to look at this carefully, this is mu of X, sorry, mu of Y. Okay, so this is the graphical meaning of what we are saying. You subtract is the same, but the mean just move. Okay, the variance the same for both cases. You subtract or minus. What's the question from the chart? No bimodal. Is yeah. Some question is asking, the card is asking why you add the two bell, is still a bell? Yeah, that is something very special. Okay. Asking why you do not see, add them up, do not see this kind of style. Not a camel. No, it's not a camel. It's actually a bell. Okay, it's a very special. That's why we need to mention. The proof, I don't put it there because the proof require a very complicated proof, which is way beyond we are learning. Okay, so just take it as given, the bell. Is it okay, Ricardo? I hope that's okay. Since we can't really prove this guy, so I think you just take it as given. Okay. Just in your head, it's just two bell together is a bell. That's it. Okay. And do note that this is not true for most cases. Okay, if you add two Poisson, it's no longer Poisson. Okay, you add exponential is not exponential. Okay. I mean, of course, if you add the two binomial with the same p, then you still a binomial. But if they're different p, then it's not. Okay, here it's like they don't need to have the same variance, different shape of bell. Okay, maybe I just change a little bit to make it a little bit more complicated, right? Maybe I make it in this way, then to make it looks like a make it different shape, right? So it doesn't have the same shape, different variance, also fine. Okay, different shape of the normal is still a normal. Okay, but of course, the variance is larger, right? Because look at the formula here, right? The variance is much bigger, right? The variance is sum of the two things. Okay, so much larger variance. Okay, actually, even you subtract, is still larger variance. Okay, so it's very surprising, right? Because you expect the two bell subtract can be very weird shape, but still still a bell shape. So actually, this is a very funny thing, right? In some sense. Okay, is there any question? Okay. Any question? I mean, there's a statement of fact. There's nothing you need to understand because you can't understand it at this stage. Okay. If you don't believe, you just try the experiment, have a bell-shaped thing. You just keep. I mean, do again, subtract the two bell, add up together is still a bell. But we don't really offer a proof for that. Okay. Now, yeah. Okay. So the rest I talk about was a chi-square, was T was F, where I don't offer any proof. Okay, I just state what are those. So there's nothing you understand or not, whether you just know it or not. Okay, so now you can relax because I need to state those facts and just need to know those facts, and that's it. Okay, we'll use those facts again. Okay, and the first thing is I'll have a chi-square distribution. Okay, and probably you want to know what's chi. Okay, actually there's a mistake in the printing. Actually it should be x squared. Okay, and they in old days x actually they refer to the z. Okay, and chi-square is exactly the z square. Okay, so basically what it's doing is we'll have a standard normal, okay, z of 0. Okay, and the question is, if I consider z square, what does it look like? All right, and a bell, standard bell, right? Whenever you take square, you don't have negative, right? So it looks like something like this. Actually, you will see that from the next slide, right? Something like this. Okay, and that is what mean by chi-square. Okay, and you only have one of those is chi-square degree of 1. Okay, you'll be clear what do you mean by degree of 1. Okay, because if you have n of these together, okay, add up, that is called chi-square n. Okay, of degree n. Okay, so if you have chi-square of degree 3, it's just 3 independent chi-square add together. Okay, and you probably ask how we use it. You will use it later, very soon. Okay, but this is something, the definition that's called chi-square, and the usage will be more clear later. Okay, so that's you need to know. Just chi-square, it's just standard normal x square. It's standard normal square. Okay, that's it. And look like this. Okay, and you don't need to worry about the density function or what, but this looks like. Okay, one is like this, and then You add more and more. Okay, you see the red one is chi-square 1, blue is chi-square 3, and green is chi-square 6. And then you can imagine that when the number of degree, this one was chi-square of k, and when k is very large, you can safely see, actually you can guess is actually when k is very large, that actually become a bell shape. Okay, but don't worry about that. But this is the chi-square looks like. Okay, you will not use it directly. This is the thing we would be defining the next distribution. It's called T. Okay, but so this is the chi-square. I hope this is clear what it is. There's nothing to learn, but just definition. Okay, the main thing is this guy. Okay, T, the chi-square, we don't use it directly. We don't work with it, but very often we'll be playing around with T. Okay, this is called T. Okay, the reason we need this will become clear in the next week. Okay, and T is defined as the following: it's a fraction. The numerator is the standard normal Z. Okay, and the denominator, something very weird, is with a chi-square of M, so sum of M independent normal, and divided by M. Okay, and this guy we define as T of M. Okay, so how many chi-square there? Then there would be M there. Okay, and this, what it looks like, this graph is a very close to the bell. Okay, and looks like this. Okay, if this is the standard normal, okay, suppose this is standard normal Z. Okay, the bell will be very similar. Okay, but with a fatter tail. So basically just like a slightly deformed shape of bell. So this look like this. Okay, it's a bell but with a fatter tail. Okay, so with fatter tail must be have lower head because you have to hammer the head and become fatter. Okay, so and you probably ask why we want to do that. Okay, and we become clear later. And many cases, okay, when we do sampling, okay, the bell curve doesn't apply directly. You have to use this slightly change of the bell. Okay, so called T. Okay, so actually you'll be very clear later. We'll be using this all the time. It's called this T, but it's just like a slightly changed bell. Okay, it's a bell but slightly changed. Okay, and that will depend on the M. Okay, so I guess I don't have enough time to talk about F, but we talk about F next class and together with Excel. Okay, so just we learned the T is a deformed bell. Okay, so I see you next week. Oh, no, so I see you on Thursday. Any question from the Zoom?